equation to show that dy dx is 3x squared plus 1 over y. So this is just a differentiation review so far. How do you do it?
Keep your focus that way to the x that you divide. Subtract x over, then do the just the x plus x.
Okay, so find the derivative of 1/2 y squared first with respect to x. So that does make it 1/2 times 2, which is just 1, y to the first power times dy dx. Right? It's implicit differentiation. You take the derivative, but you keep in mind that y is a function of x. So anytime you take a derivative y, you get a y prime. If you need a review of this, I just finished teaching this in AB Calculus, and so you have a video on your screen that says implicit differentiation if you want to review that. Minus 3x squared. No need for a dx there because the derivative of x with respect to x is just 1. Equals 1. Get all the dy dx's on one side. It's pretty easy to do on this one. And divide by y, so you get 9 plus 3x squared for y. Today we're going to learn how to go backwards. We're going to have the derivative and learn how to find the original equation. So that's going to be differential equations. Today we're going to learn about differential equations. If you've heard that word before, it almost sounds scary or intimidating. I know the first time I heard it, I was a little intimidated and then was pleasantly surprised that it wasn't too bad of a topic, at least in Cal 1. However, not even in Cal 2, but later on, if you are to go on in math, differential equations can get pretty nasty. A differential equation is any equation with a derivative involved. So it has a differential in it, so it's called a differential equation. There are 3 different differential equations there. They're at range and difficulty level. The first one, you could probably figure out the original function without me showing you anything today. Would you agree? Yeah. It's only got x's in it, so it's just anti-differentiate, right? I would have to show you anything. So, as you already know, in calculus, we often know the derivative, which is a differential equation, and need to find the original function. Sometimes the original function is easy to find, like that first one up there. X to the 4th, right? Divide by 4, 3 4 6 is 4 plus 5x plus c. Easy enough. But some differential equations are very difficult to solve or impossible to solve. Some people spend their entire careers trying to solve certain differential equations. There are important differential equations in physics, in chemistry, biology, economics, fluid dynamics, other fields. I had a professor in college who his research was in differential equations, and he teamed up with a biology professor, and he did the differential equations that modeled her MRI imaging. I'm not exactly sure how those are related, but somehow they did. There is a differential equation called the Navier-Stokes equation that is so important in oceanography that the Clay Institute will pay you $1 million if you solve it. So you can imagine the field of differential equations ranges from what we will do in Cal 1, which is probably one of the easier things you'll see, to almost unsolvable, if not unsolvable. Fortunately, the only type of differential equation that you will solve in Cal 1 and 2 is called a separable differential equation. That means basically that you can separate x and y by multiplying or dividing the differentials over. Those turn out to be actually really easy to solve, so that's great news for you. That's the only thing you have to do in Cal 1 and 2. Again, you can see that there is a full field on differential equations. So,
what's the Navier-Stokes equation look like?
I Google it. I took a whole class in college called differential equations, so you could spend some time on this. 1, separate the variables. And I'll show you what I mean by that. Step 2, integrate both sides of the equation. Don't forget the plus c. But I will tell you, we only have to do plus c on one side because we can kind of combine our constants into one. If you are given an initial condition, you will find c, and then you will solve for y. For today, we're going to leave out the discussion on domain. It does get a little bit more complex when you take into account domain. If you know anyone who is at FBLA, you might want to mention to them to watch this video. It will make tomorrow go much better for them. So notice the equation I have here is the bell ringer. Do we agree? The derivative 3x squared plus 1 over y is the bell ringer. So now we're going to learn how to take that back and find the original equation from that. Step 1, separate the variables. Step 2, integrate both sides. Step 3, don't forget plus c. 4, find the c if you have a condition that allows you to do so. And solve. Which is the same steps. Yeah,
So we just got lost as you got.
Okay, separate the variables. We're going to look at dy and dx as different pieces, different differentials. And so to separate those, I'm going to essentially cross multiply. Or multiply by the dx on the right. Either way you want to do that, but we always want to multiply that dx over. And on this one, I am literally going to cross multiply. Sometimes I may not want to do that, but let's see what's on the bottom. So I'm going to separate the variables. If I cross multiply, I get y dy equals 3x squared plus 1 dx. And then I want to try to make sure that y's and the dy's are on the same side and the x's and the dx's are on the same side. On this one, just cross multiply and cause that to happen. Sometimes you'll need to rearrange other things also. In this one, just cross multiplying, all the y's are on the left, all the x's are on the right. Any questions so far? Step 2. Integrate both sides. We are doing an indefinite integral, so we will have a plus c. We don't need it. Integrate both sides. What is the antiderivative of y? Y squared, I agree. 1/2 y squared. And what about the other side? And then I'm going to write plus c. Notice the next question kind of walks through this a little slower. Do I need to put a plus c on both sides? Yeah, I could put a c1 on the left and a c2 on the right, and then subtract a c1 over, and I get another constant. So it is unnecessary to write c twice. You could, but we're just going to write it one time. Put one constant in there. Then it says find c. What does it mean by that? It gave me that I'm going through the point 1, -2. So I'm going to put 1 in to a differential equation is always a function. So it's always y equals something. Now for today, we may have a plus or minus involved. We'll talk about where to go from there. Okay, so I'm going to multiply by 2. And then take the square root. I do get a plus or minus when I take the square root, which contradicts what I just said. Because what did I just say? The solution to differential equation is a function. Why is this not a function? It's two pieces. Now, if we didn't have a c, we'd have to leave it plus or minus. But we do have a c. We had a point we plugged in. What was that point? 1 and negative 2. Which one would give you a point 1, negative 2, plus or minus? Why the minus? Square root, right? So the square root will give you a positive value. So our initial condition, the answer is negative square root of 2x cubed. This is called a specific solution to a differential equation. If we don't have an initial condition, we can skip step 4 and solve for y. You would then still have a plus or minus. That would be called a general solution to a differential equation. So you have two different answers you could get depending on how much information you're given. If you're given enough information, you can get what's called a specific solution. If you're not given enough information, you get what's called a general solution. So this is a specific solution to that differential equation. So we're going to try a couple more differential equations. So the point that we were given, something before that, before we go there, the solution to a differential equation is always a function, just one function, something you can type in y equals and so we got a plus or minus, which is not a function. So I essentially just need to know which one was it, plus or the minus. So like if it were a circle, we're talking is the top half of the circle or the bottom half of the circle. We know that it goes through point 1, negative 2. So if I plug in 1, which one would give me a negative 2 answer? And it would only be the negative. So you pick the one that fits your specific condition. Okay, so solve dy dx equals 3x cubed plus 5. Y is 4, and x is 1. What's the first thing we do? Step 1. Almost. The dy dx, we need to separate out. We need the dx with the x's, and we need the dy with the y. Multiply by dx. So we need to get the y's with the dy's, the x's with the dx's. There are no y's in this problem. I'm going to equal that. Integrate both sides. Am I going too fast? Pretty good. Integrate both sides. So I get y. Everyone does know that the integral of dy is y. I'm okay with that. So there's a 1 there. So I should make up with that. 3/4 x to the 4th plus 5x plus c. I would always, even before I got y by itself, with this one it doesn't matter why it's already by itself, but I would always go ahead and plug in the initial condition first if I have that option. It's usually a little easier to do before you solve for y. Just saves you a little effort and some nasty square roots and things. So I'm going to plug in 1 for x and y for 4 for y. Common denominator over there on the right, 24ths. 5 would be 24 fourths, 23 fourths. Subtract that from 4, which would be 16 fourths. So negative 7 fourths. So y is 3 fourths x to the fourth plus 5x minus 7 fourths. That is a solution to that differential equation. This next one needed to tell you one other thing. They needed to tell you that k is a constant. But you kind of know that based on it not being a variable in dp over dt. Does everyone see what I mean by that? So dp over dt equals k times p if p of 0 is 20. Let's have an extra variable for it. This is actually a very, very, very important differential equation. Very common. It is so common that we will memorize how to do it at some point. No. You'll just need it. You'll just want to, rather than having to work it out every time. This one I won't have to make you memorize. You will probably choose to, because otherwise you'd have to do that. We won't have a new mastery exam until BC. Okay, so I need to separate variables. P is a variable and T is a variable. That does mean that K is a constant. So because I don't particularly enjoy fractions, I'm going to leave K where it's sitting and call this dP over P equals K dt. I need to divide by the P and multiply by the dt. And you can do that in multiple steps if you need to. But you need all of the P's on the left and all of the T's on the right. Integrate both sides. God, pretty quiet today. How is this? Is it? Okay. Integrate both sides. What is the antiderivative of 1 over p? Natural log of the absolute value of p equals kt plus t. So far, so good. Put in 0 for t and 20 for p. Everyone agree with that? 0 for t, 20 for p. So c is the natural log of 20. Do you need absolute values on that? This is the natural log of 20, right? So we can ignore the absolute values. We're not ignoring them. We understand that we don't need them. Does that make sense? Natural log of 20 or the natural log of the absolute value of 20 is the same thing. So we have natural log of the absolute value of p equals kt plus natural log of 20. We need to get p by itself, correct? So we're going to do it will soon if it doesn't yet. E to the kt plus natural log of 20. A couple of things. initial condition because we know that we don't have pluses or minuses in solutions to differential equations. Our p-value was a positive 20. So what does that mean here? It's just a positive. So I'm going to get rid of the negative one. Again, I'm not completely getting rid of it. I'm just saying it for my initial condition, that was not the solution. So it is the positive value. Okay. There's nothing wrong with this answer. Most of you would stop here. But we're going to do a little more work. When you have an exponential with addition in between, e to the power plus another power, right? Doesn't that really mean that you could break this up to be e to the kt times e to the natural log of 20? Properties of exponents, wouldn't that be the same thing? What is e to the natural log of 20? This is the perfect formula. 20 e to the kt. In fact, anytime you have constant times the y value, where the y value is multiplied by constant in the differential equation, then your solution to that differential equation will be your formula. Will be a continuously compounded growth problem. We'll do word problems with this later, a couple days from now. So for now, this is the first time we saw it. So we'll spend a little more time specifically on exponential differential equations. Okay. Probably the last one for the day. I gave you a pretty good hint on this one on the last problem. First of all, see if you can tell me why it's difficult, and then see if you can.
E exponents y.
Okay. So maybe it's not so difficult. Maybe I'm wrong. Okay. So I heard some of you mention that there might be a way to do this. At first glance, this looks like one of those impossible to us problems because it looks like I can't get the x and y apart, right? If you ever come to one that truly you can't get the x and y apart, then you can't do it. That's not a Cal 1 or Cal 2 differential equation. So if I am supposed to do this, then there is some way to get the x and y apart. I can rewrite this as e to the x divided by e to the y. Which actually turns out to be a pretty easy equation, doesn't it? So e to the y dy equals e to the x dx. So this is a hard differential equation. Now what? Because you added that up. Anti-differentiate e to the y, everyone agree? Equals e to the x plus c. Any questions so far? Did this one give me 0, 2? Is that what that says up there? Okay. So when x is 0, y is 2, what's anything to the 0 power? So e squared minus 1 is c. So my equation is e to the y equals e to the x plus e squared minus 1. And properties of logarithms. Is there a property for this?
Maybe.
That's the question.
What are we doing?
Is there a property of logarithms with pluses and minuses in the logarithm?
Oh, properties of logarithms. There. No, not in it.
No. Don't make up properties of logarithms that don't exist. So there is nothing you can do here, which is fine. I'm completely okay with looking at it that way. Is it a function? I'm good. Done. Me and finish. We'll talk about domain tomorrow. If you come to a question in your homework that asks domain, I will talk about domain tomorrow. There are some that ask domain. You can work them all the way out. Just don't try to answer the domain question yet. We'll talk about that tomorrow when everyone's here. It's a hard enough topic. Like it's not that hard. I don't know. So we'll talk about domain tomorrow. I think that you can start on this. It does tell you to do page 331, quick review. It's very rare for me to assign that. It was on purpose. But I want you to completely ignore the directions and just solve for the general solution to the differential equation on those. So just find y general solution, because they don't give you points or anything. Wednesday, because you have to learn how to do domains before you can. Any questions about what we're doing right now? Tomorrow we'll talk about domain. We will have to grade your AP Cat more tomorrow, and then we'll spend the rest of the week on differential equations. This is the last new topic before your next exam. Any questions? There's more to it though. We're not done.